Okay, welcome. Welcome to our morning breakout session titled How Engineers and Entrepreneurs Are Building Resilience in the Grid. As the climate changes, utilities and innovators are reimagining how our electric grid is designed, financed, and managed. Today's session will take us inside that transformation through an economist lens, exploring how updated engineering standards, smarter software, and evolving market incentives are driving a more flexible and resilient grid for the future. I'm pleased to introduce our moderator, Professor Chris Knittel. Chris is the George P. Schultz Professor of Energy Economics and Associate Dean of Climate, Energy, and Sustainability at MIT Sloan. He also leads the MIT's Center for Energy and Environmental Policy Research and the New Climate Policy Center. Finally, Chris is the director of the Inventing New Policy Approaches mission for the Climate Project at MIT. And transparently, that was the paragraph I was sweating over all day because you have so many titles, Chris. We're thrilled to have you here with us, so please join me in welcoming Chris to the stage.
Great, thank you very much. Super happy and excited to be moderating this session. I'm going to call up the speakers. Why don't we just do that now, and I'm going to let them introduce themselves. And the plan is I have about 10 minutes of prepared remarks to kind of set the stage, and then we'll just have a conversation that will include the audience as much as possible. So Lisa, you want to start with an introduction?
Yep. Good morning, everyone. I'm Lisa Salmore. I am the Vice President of Asset Management and Engineering for the electric network in New England for National Grid. So my team oversees the system planning aspects, so they look at system load growth, customer connections, and make sure our system is ready for all those connections and those changes. I have asset managers that are looking at the health and asset condition of all of our assets in the field, whether they're transmission lines, distribution lines, substations, and prompting projects when they need to be replaced. And then I have project engineers who are working on the actual projects, designing the overhead transmission system, underground transmission system, substations, protection, telecom, metering, all the good stuff. So I have a bunch of brilliant engineers on my team doing very complex work.
Pablo?
Good morning, everyone. Pablo Ruiz, I'm CEO and CTO of NewGrid. I'm also a consultant at the Bravo Group and I'm in the research faculty at BU. At NewGrid, we offer like a Waze or Google Maps for the grid. So whenever there's congestion, our software technology finds ways to reroute flows over the existing network. The rerouting is done leveraging the existing infrastructure. So the idea is to get more out of the existing assets.
And Chris.
And I'm Chris Rezendez. I'm the Chief Business Officer of a company called Context Labs. I was spun out of MIT, work that our founder Dan Harpel did here as a fellow. We're a climate AI platform. What does that mean? Our clients deliver to us data from systems of record. We enable them to create secure digital twins of their assets in the physical world so that we can help them achieve, prove, and profit from their ability to manage safety, operations, and climate impact of those assets, either by way of truly counting carbon emissions or truly proving the source of a green kilowatt hour of energy. We're headquartered in Amsterdam. We have a huge presence here in Kendall Square, always will, and we're just really pleased to be here.
Well, that's great. If I could have you sit down, and I'm just gonna, maybe I don't have to do this for this audience, but try to convince you that the grid is a major bottleneck, not just for decarbonization efforts, but also affordability reasons, as well as resiliency reasons. So I put together a few slides. I have 30 slides in 10 minutes, so I'm just gonna talk really, really fast. So obviously, with the events that happened last week, or maybe it was even this week, in Spain, the grid, that event, as well as other events in the past, just point to the fragility that the grid can sometimes represent in our electricity system. So if you haven't followed Spain, which you probably did, but within 5 seconds, 60% of Spain's power plants went offline. They're still investigating what happened there, and then for the next 10 hours, the grid was completely shut down. From all accounts, they did a brilliant job with what's called black starting the grid, and getting it online in 10 hours was actually quite a feat. We had a similar potential issue just a few years ago in Texas. So the right graph there shows the frequency of the Texas grid during Winter Storm Uri. And to level set, what that is the frequency of the grid. And if the grid gets below that blue line there, things start to go really bad. So what happened in Texas is a freeze froze a bunch of natural gas lines, which led to those natural gas power plants going offline, as well as froze a bunch of wind assets in the grid. Now, Texas was able to, the ERCOT was able to save the situation by shedding load as quickly as possible. But what that also led to were multi-$1,000 prices for electricity on something that usually trades in the $50 range. So that just shows that the grid is an asset that constantly needs to be not only monitored, but improved and upgraded. There's a bunch of problems with the grid right now. One of which is if you build a new solar farm or a wind farm, in many areas of the country, it'll take you 4 years to be able to interconnect that solar or wind farm. So clearly, if we often talk about these 2030 or 2035 goals in terms of decarbonization. We just can't get there if it's going to take multiple years to interconnect those carbon-free assets into the grid. Recently, FERC issued FERC Order 2023 that's trying to address that, but shameless research plug here. We have a paper in Science that basically talks about what is lacking in that FERC 2023 order, and that there's still a lot of policy levers that need to be pulled if we're going to correct the interconnection queue. This is a separate but related issue, is that we just don't have enough transmission lines. So DOE recently did a study that calculated how much transmission capacity we should have in the grid and compared that to the utility plans for building transmission, both the short-term plans and the long-term plans. And you can see in many parts of the country, the utilities are lagging behind what the DOE believes we need to be building. For Lisa's sake, I'll say that the Northeast is doing quite well, so congratulations, Lisa. But in other parts of the country, we're just not building enough transmission lines. And what that's leading to is higher costs. So this is a graph of congestion costs that are borne ultimately by consumers over time. And you can see on average, at least, they've been increasing over the past 8 years or so. So not only is the fragility of the grid leading to potentially catastrophic outages, but it's leading to higher costs to consumers, and it's leading to lower decarbonization rates that we might otherwise have. That's also being borne out by, if you build that solar farm and you wait those 4 years to interconnect, you'll often have to curtail your power from that solar farm as well. Why? Because there's not enough transmission capacity to move your electrons to other parts of the country. We're terrible at building more transmission lines. One of my colleagues often says, anything long and skinny is hard to build in the United States because it goes through lots and lots of people's properties, and by and large, they have veto rights on building that line. So one of the exciting things about this panel is when there's issues, there's also opportunities. So one of the things we want to dive into is how these organizations are overcoming these bottlenecks in the grid. Despite the fact that we're not building transmission lines, we're spending more and more money on the transmission grid. But that money is going toward basically hardening the grid, such as undergrounding transmission lines and so on. So we're spending a lot of money, but we're not necessarily expanding the grid. And why do we have to do that? Partly because of climate change. Climate change is leading to a lot more extreme weather events, whether it's hurricanes that are slower and wetter that cause more flooding, whether it's wildfires. The connection with tornadoes is still being studied among climate scientists, but there's at least some belief that climate change will lead to more clusters of tornadoes as opposed to more tornadoes on average. And it's the clustering or the cascading effects of multiple tornadoes that are likely most damaging to the grid. I'm a policy guy. You heard all of my titles. They all have the word policy in them. So I like to think about how public policy can overcome these bottlenecks and these issues in the grid. And I will say policymakers are trying hard. Just within the last few years, there's at least 5 bills that were proposed in Congress that in some way, shape, or form try to address the fact that we need more transmission in the grid. We've done a lot of analysis using MIT research tools to help those policymakers study the impacts of those bills. That's the new MIT Climate Policy Center, which I'll just give a brief plug for. The MIT Climate Policy Center is not about generating new research. We feel MIT is already doing a lot of great research that basically dies on the vine. It's not being picked up by policymakers and being turned into actual policy. So the idea behind the new MIT Climate Policy Center is to take the research that we do here at MIT, hand walk it over to the policymakers, and work directly with policymakers to turn that into actual policy. And these are just a few examples where we've worked with members of Congress to use the capabilities here at MIT to model their bills, to propose new bills, to understand what the impacts of legislation might be. And one of the things we found in that work is around resiliency, that we often think about building transmission lines to reduce costs or perhaps to speed up decarbonization. But what we've been able to show through that research is if we could build out more transmission lines, we will be much more resilient to the Winter Storm Uris or the recent storms in the Carolinas. What these numbers show is the % reduction in outages that fall from building more transmission in two potential ways. Happy to talk about that during Q&A. But what we've also found with this work is that we're really bad at building transmission. So this is a study that's not yet published, and there's a lot of numbers on there, but if you focus on that last column, that's how much more as a multiplier we find transmission is to build over what the engineers say it costs to build. So as an example, if we want to build a transmission line from the southwest US to central US, the engineers might tell us it's going to cost X dollars per mile to build. We find it actually costs 14 times that to build. That's the extreme there, but you could see almost everywhere in the country is above a multiplier of 2. That is, it's twice as expensive as what it should be to build more transmission. So in the face of that, what do? We could pass new legislation that makes it cheaper, or we could have smart people that overcome those bottlenecks through data and through smarter ways to actually run the grid. And that's what we hope to delve into now into the panel. All right, I actually didn't do too bad. Okay, all right, so I'm gonna move over here now and basically ask our panelists to go down the row and talk about where they fit, their organization and their work might fit into some of the issues that I just raised. So why don't we start with you, Lisa?
Yeah, and I have a few examples to share, both on the transmission and the distribution side. So on the transmission side, as Chris noted, right, there's a lot of spend in transmission. For our particular company, most of what's driving our spend on the transmission side is asset condition related. So for example, we have a project right now that's replacing a transmission line that was built over 100 years ago. It was one of the first transmission lines in New England. It's called the A1B2. It's a 69 kV double circuit transmission line. And due to asset condition, wear and tear over the years, it's time to replace it. So what do? Do we replace it with the same thing? No, not a chance, right? So we're looking ahead. We're looking at forecasts that look out to 2050 on what's the current load forecast and resilience requirements, and we're replacing it with a 115 kV structure, a double circuit structure. So it's much taller. And just this week, a tree fell across both of those transmission lines, and we had an outage, and customers didn't have power for a few hours until we took the tree off. With the new structures, they'll be much taller. They can avoid some of the tree contacts, and it's fit for future growth, whether it's load growth or connections that are happening with large load or other customers. So when we are touching our assets, whether it's because of asset condition or other reasons, we look ahead to make sure that we're building it robust enough for its lifespan, because that transmission line could be there, the new one could be there for another 100 years, hopefully longer. So we want to make sure we don't have to prematurely go back and replace it. From a climate perspective, we know where coastal flooding is happening, and we know what substations are at risk for flooding, which can tremendously damage our electrical equipment. With climate models, we can overlay, what are the different climate scenarios over the next 50 years, and that coastal flooding goes further inland. So what other substations do we need to worry about? And as we're replacing them over time, we build into our standards and raise the substations, or look at opportunities to relocate the substation out of those risk areas. So as we're touching our assets because of asset condition, we are looking to build them for the future based off of a lot of data, a lot of information, a lot of forecasts and scenarios, so that they're robust enough. On the distribution side, I know you talked a lot about transmission,
Yep.
but distribution is what impacts our customers. So we have 1.3 million electric customers in Massachusetts, and our transmission system is built quite robust. It's N-1 contingency, so you can lose a couple elements and still supply power to the region. On the distribution network, it's localized, right? So if you have one tree fall, you could have customers without power. And so how are we combating that? We're looking at automation, self-healing networks, to figure out how we can operate the distribution network quickly to restore as many customers as possible. When our system was built out, the distribution, it was built in a radial fashion. So it was a single distribution line that would start at the substation and go to the furthest customer. And if a tree were to fall at the beginning of that line, everybody would lose power at the end, to the end of the line. So what we're deploying now, it's called FLISR. It's fault location, isolation, service restoration. So one of our fancy acronyms. But the first step is looping those radial feeds. So they're loops so they can be served from different substations. And then there's sensors and automatic devices on the network. So if a tree were to fall in a certain segment, a bunch of operations happen that everybody on that segment would have power restored within a few minutes, except the customers that are really close to where that tree fell. So we've deployed that in about 23% of our network right now, and we started that in 2020, and over the last few years, we've saved over 28 million customer outage minutes because of the operations of that self-healing network that we have, and we have plans to deploy that across our distribution network. So that's like a real-time, how can we protect our system and protect our customers from outages, and that comes into play when we have significant wind events, because the trees are most, we love trees, but they're also our worst enemy when it comes to reliability, because it's usually the trees that blow over and take out our system during a weather event.
And before I turn to Pablo,
Yeah.
just a quick question. Right now among the policy community, there's a lot of focus on affordability. And unfortunately, as the climate is changing, it's forcing companies like National Grid to do a lot more than they used to have to in terms of hardening their assets. Are you feeling the pushback yet from policymakers or customers in terms of this trade-off between a more resilient, more reliable grid and maybe a slightly more expensive grid?
So on the distribution side, we have, I guess, two different plans, and our base plan, our rate case plan, is mostly around reliability. It's targeting the assets that need to be upgraded to ensure we can minimize outages to customers. There's been no pressure, right, on that, if not pressure to do more, and you know, trees, right, are the biggest impact during a storm and cause outages. Some folks would challenge us, why don't you underground the entire system?
Right. Ask PG&E.
It's really expensive, and that shows up for ratepayers. So there might be optimal places where we know it's optimal and it's cost effective to underground it instead of go back and replace the pole over and over again, but it's not necessarily our entire system. So programs like the FLISR, the self-healing network, and then other devices and information we can use, whether it's sensors to get the most information to make the best decision, that are optimized. So we have one sensor that we're deploying now is early fault detection, which are sensors that sit on the structures and they can sense if there's an abnormal condition on the distribution line. And through analytics, it can say, oh, it looks like a tree's brushing up against it, or an insulator might be broken. And then we can send out a crew before the outage occurs. So that's the type of stuff that we're getting pushed and want to pursue, because it's a lot easier to hang up a sensor and proactively avoid an outage than to underground, 18,000 miles of distribution network. Our other filing is around electric sector modernization, which is our plan to build out our network for electrification of EVs and heat pumps. And that's the one where, depending on the affordability and the pressures, we're hoping to see a favorable outcome to that in the next couple months. But that's probably where we'll start to see the pressure if there's an outcome that's not in line with what we're hoping for.
Great. And your point about sensors and transmission lines is a perfect segue to Pablo. Pablo, do you want to tell us a little bit about New Grid and what you're doing?
Happy to, thanks, Chris. So at New Grid, we are focusing on the transmission congestion management problem. In a little bit of background, the transmission versus distribution. Transmission is like the regional highway network on the power side. Distribution is like the more local roads. The transmission network is a highly redundant, very robust. It's planned and operated to be able to sustain faults and maintain service to entire regions. Now, it's mostly a free-flowing network. So if you, by and large, there are exceptions, but by and large, if you inject power in one location and extract from another location, Kirchhoff laws will determine how the flow distributes among the entire network, rather than explicit control of where it goes. So on the other hand, the transmission limitations, and we've heard about bottlenecks, certainly the grid is a bottleneck in different ways. Those limitations tend not to be electrical. So these are almost orthogonal. So these tend to be independent of the laws that indicate how the flow will go. So if you combine those two, you end up with very few bottlenecks at any one point in time, limiting transfers across entire regions, where most of the network has additional capacity under those particular conditions, which change all the time. There could be outages. Lisa mentioned some examples. In a world with higher solar, when there's more volatility, extreme events really shift flows. So it becomes a much more a dynamic environment. So the traditional approach to manage that congestion has relied mostly in a redispatch. That means in a change in the production of generation across the system. If we make an analogy with a highway system, that will be equivalent to raising the tolls for certain people to discourage them from driving until enough decide not to drive. That's an expensive approach. Chris showed some charts of the congestion costs. What we have been working on is to mitigate those impacts by changing the grid itself. So our goal is to adjust the grid, opening or closing existing circuit breakers, to reroute flows around the bottleneck, much like a Waze or Google Maps would do for drivers. And
So not the physical grid itself, but just how electricity is flowing across the grid. You're not building new transmission.
We're not building new transmission. We are using
more
it
efficiently.
more efficiently given the system conditions. So
Yep.
which change all the time. And when you do that, what we're finding is that you can move anywhere between 5, 10, 25, sometimes 50% more flow over the existing wires, accounting for everything else that might be on outage. And so you can imagine the level of impacts in terms of congestion cost, avoiding curtailments. Our estimate is that 50% of the cost that you showed could be reduced. That speaks to affordability, that speaks to accelerating the energy transition and so on and so forth.
And that is even absent, there's been a lot of work recently on the academic side about what's called dynamic line rating. Basically, we often run these grids as if the capacity of a line is stagnant, yet in practice it depends on weather conditions and how you're using the rest of the grid. So are you getting these reductions even absent that? So if we added dynamic line rating,
then that creates more room to reroute even further. So
Yeah.
Absolutely.
Okay, great. And I notice many of you are submitting questions in the app. Keep doing that. We're going to go to Chris next, and then I'll start to bring in Q&A from the audience. Chris.
We're thrilled to be here. I'm going to start maybe at the top, close to where you were, is that there's a new paper out, a guy named Jeff Curry, who I think is a fairly well-recognized authority on global energy markets. And what he writes, the main thesis is that when we think about energy markets, we should perhaps shift focus from the production to the effective application of the load, which means transmission and distribution. Because many of the challenges to economic development or national security or grid resilience happen not at the production sites necessarily, but through transmission and distribution. So the concept is called the joule economy, or the delivered joule, which needs much more attention. I think what you're doing here today is diving into a couple of those places that Jeff and the global markets are now starting to pick up. It came out at CERAWeek, and I unfortunately travel too much outside the country. My family's not so happy about it, but I can tell you, like everywhere I go in the GCC or in the EU or even in Asia, the large energy companies are talking about not just their production, but their partners' ability for providing the transmission and distribution, essentially the effective application of a joule. And I think part one. Part two is that requires, based on what both Lisa and Pablo said, an extraordinary situational awareness, not only of your own assets and their existence and their identity, because we know we've got problems in these large, skinny asset bases because they're highly distributed and they're not very dense, and sometimes energy companies don't even know what the accurate inventory of its asset base is. So the second thing I'm going to say is situational awareness is critical, not just for your own assets, but for those assets upstream and downstream, for the maintenance events that could interdict performance, and as well as the externalities of weather. So there's a need to have, I think, finer grain, higher frequency, higher resolution data sets about these different dimensions that could impact delivery of the joule. And finally, I just don't think we have enough really bright people who can stand at each of these assets and monitor it and observe it with their phones and with their notebooks. So where I'm getting to is our business. You've got to have another digital infrastructure that enables you to create not big overwrought digital twins and not data for data's sake, but we need a new appreciation for the fact that this critical infrastructure is a cyber-physical infrastructure, not just physical. And the digital systems that are monitoring and enables us to manage are going to be key for our ability to respond to what we know. And Lisa brought something up brilliantly yesterday, which is, in a way, we would like to see utilities be as innovative as, say, the tech companies, but at the same time, let's recognize you can innovate digitally and break nothing. If we are expecting National Grid to deliver 3, 4, 5 nines of reliability in a cost-effective way, in alignment with these regulations, and observing some of the things that Pablo's new grid are enabling you to do, we can't afford to experiment in the physical world. So we've got to be able to experiment in the digital world. And that becomes, I think, another reason, I think, for us to be here, which is to say, we need stateful, secure delivery of systems of record data, not only so that we can manage and monitor the assets, but so that we can take advantage of this thing called AI and start to innovate rapidly, so we can enjoy the benefits of the innovation without taking on the risk in the physical world. So I know that was a lot, but it is the whole energy system. We have a much more acute need to monitor so many more variables. And I think the only way we're going to do it cost effectively, to your point about financial resilience, is if we start to pay attention to the right digital systems that can inform the physical assets.
And Chris, so you sold me, right? So I'm ready to write the check, but what's keeping everyone from adopting this technology?
Well, so I think there are 3 primary limiters. So we are obsessed with the carbon intensity of the assets that our clients operate. We believe carbon is the next great operating variable. We believe carbon intensity is the next great product specification. And we think sooner rather than later, primarily the debt markets are going to make it the next great input to risk and rating and pricing. So 3 things are inhibiting this, I think. The first is the digital maturity of the physical asset owner and operator. They are physical entities run by physical engineers working in the physical world. That's a hard model to break. The second one is, at least for our business, and maybe even in the other businesses here, what is the definition of performance? And if it doesn't include some of these next generation dimensions of resilience, like climate or carbon, if someone's not at that level where they understand resiliency within this externality of carbon, then they're probably not going to do it. And then last but not least is, who's going to pay for it? If this is seen as another compliance requirement, then it's considered GRC, and then it's all about who's going to pay for it. So I think those are 3 primary reasons. What gets us out of it is having data that backs the claims that the physical asset owners and operators make, so that their commercial and capital markets partners will pay them for it. In other words, we shouldn't see climate performance the way we saw grades when we were little kids. Hey, don't pay kids to study, don't pay kids to get an A, you're undermining like the reason for people to study. I think in this market, those companies that better manage carbon, for example, or resilience of an energy grid should be paid more. I think that's the only way you're going to get more adoption, is to show that there is a straighter and brighter line between the metrics of these performance dimensions and what the income statement and the balance sheet show.
And absent policy, that I guess we hope that these less formal carbon markets are what's providing an incentive, or you have the tech companies themselves have their own carbon goals that are more aggressive than necessarily they have to do.
So I'll short answer, and I think we should go to Pablo and Lisa on this, but here's what I'll tell you. The private markets will say, we have 2 choices. We either pay taxes, fines, and fees to governments, or we pay ourselves to manage this in private markets. So industry trading groups have standards, individual buyers, lenders, and investors have their own methodologies, but it is a formalization with the data to back the claim that I think these private transactions will invest in. And I think the private markets would rather see those additional dollars and euros and yen and et cetera move in and among themselves than send them into public coffers.
And to link it to Lisa, I know the PUCs regulate you on different metrics of resiliency, like SAFE and SAIDI and so on. And then another part of National Grid is regulated under a renewable portfolio standard that has to show carbon intensities. How much linkage across the organization is there in terms of talking about both reliability and maybe the data and carbon intensities that Chris is talking about?
I would say, from my perspective, they're connected when we begin to talk about our standards.
Yeah.
And then the standards are the specific equipment we select to install, like SF6-free breakers, and there's there's incentive there, but it doesn't necessarily map to reliability.
Right.
At the moment.
Yeah.
Because the reliability metrics that we have, the SAIDI, the SAFE, it's how many customers are interrupted and for how long. There's penalties that loom over any regulated business to perform and stay above a certain level for our customers. There's no incentive right in there, and then the greenhouse gas and compliance. That's more of standard decisions, like I said, what equipment we're ordering and how. What are the impacts of that? But there's not as much like incentive or disincentive to do that. So it's been more of our corporate decision. We want to eliminate SF6 from our assets, and what is our plan to do that? But it's still within it needs to be cost competitive, right? We can't spend twice as much on a SF6 breaker than a non-SF6 breaker. So those are the types of decisions that are coming to my team.
Okay. And Pablo, just trying to link you to what Chris is talking about, it sounds like your technology can optimize on many different levels, right? You could optimize on costs, you could optimize potentially on emissions. Your clients, what are they optimizing on, or what are they asking you to optimize on?
Great question. So usually when you're optimizing on cost, you cover several other dimensions. Sometimes you don't, and there could be some metrics that are kind of hidden. So by and large, we look to mitigate congestion costs, but at times we may be receiving requests to enhance the deliverability of, or let's say, a solar plant or a wind plant that otherwise would be curtailed. We've seen some of those charts. Sometimes the request could be counterintuitive. So some of our clients have a diversified portfolios. It could be that they have some plants in the quote unquote good spots of congestion. So whenever there's congestion in a normal market like in the US, the sending end will have a depressed price, the receiving end will have a higher price. So if you have plants on the higher price, you would assume that that's a good thing. Sometimes we get requests from clients that have plants in those locations indicating, well, I have a coal plant that is seeing upside congestion, but I would like to not run it. We would like to conserve the coal or rely on our other assets. So there could be environmental reasons there too. So you never know, but in general, the congestion bottleneck materializes in a number of different fronts.
Got it. So I'm going to turn to the audience questions. They're much better than the ones I prepared, so thank you very much. So the first one that, not surprisingly, has a lot of upvotes is around cybersecurity. And so you all talked about using data. Chris, you talk about digital twins and so on. Is there a risk as we use these data more, as we use your technology, Pablo, more, that cybersecurity attacks could be more problematic, or do you actually view yourselves as actually providing more resilience to cyber attacks? And Lisa, to you, how much do cyber attacks keep you up at night?
Yeah, I'll start. I think it's probably an outdated number, but I think we have around at least 1,000 phishing attempts daily. To try to.
What do those look like?
Sometimes they're just emails getting you to try to link in things, or more nefarious actions, like trying to get into our control centers, right? So,
okay.
I know our CEO John Pettigrew. It was probably a year ago. Somebody asked what keeps you up at night, and he said cybersecurity, because it changes. The attacks change, the methods change. It changes so quickly. That's the one thing that we have to keep up with, as a utility. And we're working with assets, right, that are 100 years old, that have been in the ground for 100 years, and now we have this daily attack that's changing. So it keeps all of us up at night, because an attack could just wreak complete havoc.
And it's not just your assets. If you think about it, if a city block has all EVs sitting in the garages, and somebody attacks those EVs to all start charging at the same time, and transformers start to blow up, and how do you manage the fact that almost everything is connected to the internet now?
And it's not bidirectional. It's just it's integrated. So so the points of entry is becoming more vast the more connections we have, and the more not just physical connections with EVs, but with the different systems and the technology that we're using, third parties that we're using to either host data or control our network. It's concerning, right? We have a robust cybersecurity team that works diligently to address any attempts and attacks, and make sure that our system is robust enough to defend that.
Mm-hmm. Pablo, to you, does using your technology make us more or less susceptible to potential cyber attacks?
It's a great question. It makes you significantly less susceptible. So early on in the formation of NewGrid, we decided that we would offer decision support or advisory rather than control support. So in other words, our software doesn't control anything, but it provides the options to operators that then can validate that the options are legitimate and are reliable using their existing systems. So there is that gap between, we're not controlling. But then in addition, because we're performing similar type of calculations as the existing systems, we were effectively providing redundancy in those calculations. We, a fully independent calculation to validate that, what we are seeing in the EMS, comports with what you are seeing on the NewGrid side.
And could you, in theory, simulate cyber attacks on your clients' grids and try to understand how to provide real-time capabilities?
We can simulate this, how to respond to a series of disconnections that could be a result of an extreme event, cyber or otherwise.
Right.
And in fact, we have done work, working in the Midwest, for example, during a major winter storm Elliott. We had been working in that area already when the storm happened. And some of the solutions that we were identifying were deployed during the storm that enabled additional generation that would have been behind bottlenecks to be delivered to end customers. So that's another illustration of the benefits.
Yeah, and Chris, where does cybersecurity show up in your?
I think it's. I'll be cute for a minute. I know I'm at MIT, but I'm going to try to be cute. Remember the adage: if you think education is expensive, try ignorance. If you think cybersecurity is expensive, try breach or hack. I love what Pablo said. Our view as a system of reference is to stay away from the systems of record. So respect the stateful nature of the real-time control systems in the grid, part one. Part two is you've got to have a strong supply chain. So those that are in the software hardware business, you've got to have controls in your supply chain of the software tools and or the hardware tools that are coming into the system. Second is you've got to practice that sort of stateful activity. We stay out of the control plane. And I think the third thing is that there's a concept called automated coordinated action. Comes out of an NPPD white paper from March of 2013, which is a declassification of a white paper that was written by the folks at NSA some 10, 12 years ago. And what it basically did is started the concept of homomorphic cyber-physical security systems. What is all that gobbledygook? You have to distribute security as far and as wide into your networks, plural, as you can, so that you can start to have more data flowing among and between those entities, and then you can start to put more decision rights in a more distributed fashion. So, in other words, to have an agile, resilient grid, you've got to enable more data to flow among and between the entities that are trusted on the grid. You've got to enable those entities to make more and better decisions. So in other words, you can't centralize security. It's not a one-time thing. It's got to be persistent throughout your cyber-physical asset base. It's got to be persistent through all of your operating or development systems, and it's just got to be a constant running in the background. Because I think at the end of the day, that too is going to be another risk factor when credit analysts are looking to rate and price and allocate. Is a more secure grid is going to be a more valuable grid, the same way a lower carbon intensity grid will be as well. Cyber's got to be seen as a new performance dimension, I think.
So not surprisingly, we have a lot of votes on trying to think about what we can learn from the Spanish and Portugal experience of the last week for US grids. I'll just start by saying we still don't know what caused it. I think Spanish policymakers have given the grid operator, I think, 3 months to understand what caused it. The leading explanation in the clubhouse is probably a disruption in the main transmission line that connects the rest of Europe and the Spain-Portugal peninsula. But I'll just ask our three panelists, what can we take, even though we're still trying to understand what caused it from the Spanish?
Yeah, we're chomping at the bit to understand because whenever there's an incident that happens on any electric network, we're looking at that and identifying what's our risk and what are our mitigations and protocol and how would we respond, how would we prevent. So whether it's wildfires or I think there was a couple of years ago there was a ballistic people shooting substations down further south, and so it's like, what would our response be? How do we prevent it? So we're chomping at the bit because we want to know so we can test our processes and test our emergency response plans to make sure that we would be prepared. But depending what happened, right, that might be a conversation with just us, with National Grid. It could be a conversation that we have with the ISO, with the independent system operator in the regional network. And everybody's chomping at the bit. I think EPRI, which is the Electric Power Research Institute, it's a great research institute that we work with occasionally. They've already set up meetings to have a discussion. The North American Transmission Forum, they're setting up meetings to have a conversation, and we're all ready because we do want to understand so that we can avoid and prevent a similar situation.
Yeah. Pablo, what do you take from that?
So we're still learning, but a couple of takeaways would be that cost-saving measures on analysis and then adaptation and control is very short-sighted. So I think we have seen traditionally the utility industry has been regulated on cost rather than performance, in spite of National Grid's best effort to do incentive-based regulation. But when you have the frame of mind of saving cost, that percolates to all of your decisions, including on operations, and we are operating in a very different environment. It could be that the same event that maybe a decade ago would have done nothing, could have other phenomena. Now, to understand those other additional phenomena, you need different systems. You might need a larger team, or with different skills. So, being mindful of those aspects is super important.
And Chris, before you answer, I want to bring in another question from the audience, which is, since you are a very much an international organization, how does the U.S. grid compare to other parts of the country or other parts of the world? And you could punt on that if you want to be politic and answer the Spanish question.
I think it's, from a reliability perspective, probably much better than average.
Yeah.
From an efficiency perspective, it might only be average. From an affordability perspective, I couldn't say, because in other parts of the world, they're not necessarily publicly traded securities, so you don't know what the financials are. But I'll go back to something I think all of you have said. The only thing I've read about what happened in the Iberian Peninsula is that the black start capability was the key to getting power back.
Yeah.
And so if you put black start capability into these kinds of concepts of how paranoid are you about what the interdictions might be, how focused are you on resilience and investing in resilience and what the payoff of resilience might be over time, I think we start to get to the concept of distributed, decentralized grids, not a grid, the same way we try and deal with digital networks. There is no the internet. We are in splinternet. We've been in splinternet for about a decade. It is networks upon networks upon networks, and I think the view of our electric grid that way could be a great framing for people to understand what kind of investments they're making and what kind of offtake agreements they want to sign. I think one of the best things we can do is start to expose that kind of distributed resilience capability in those black start networks and start to invest in energy companies that do that. That was a plug for you, unintentionally, and actually start to see National Grid and Lisa's work in a different light. It's not all old rusty, dusty steel, concrete, and cables. There is incredible investment taking place in the background. Most of it's in the digital sphere to enable the innovation, to be very particular about the big physical investments. But what I get out of what happened in the Iberian Peninsula is you have very different responses when you get into those different distribution networks. And I hope that the analysis looks at not only root cause, but about the elements of the networks that responded well or not.
Right, yeah. Yeah, I showed the graph of Texas that was able to kind of get out in front of the problem before it actually led to.
And what was one of the keys to their network, right? Optionality.
Yeah.
They had many different options, not only for production, but also for transmission and distribution. They had built in these certain optionalities, and that's something that I don't think every network operator truly understands.
Yeah, and Texas is interesting. For those who don't know, they're not interconnected to the rest of the country. That's on purpose, so that the federal government can't regulate them through the Interstate Commerce Clause. So in some situations, it might provide less resiliency, but the absence of that federal regulation, they argue, allows them to be more nimble in things like this. The other topic that came up quite a bit in the voting is around data centers. So maybe we'll start with Chris and work our way down this way, but I'm just wondering what's your organization thinking about in terms of data centers? And those are the data centers that often want to be very aggressively decarbonized. Correct. And is that the service that you're providing?
So yes, that is one of the services we're providing. So I think data centers, we might consider them to be the next major element of critical infrastructure. If it's energy communications, water, wastewater, transportation, we might now start to conceive of or consider AI infrastructure as another major infrastructure element before we start to get into health, education, and public safety. And then I think we can't talk about AI infrastructure without talking about carbon infrastructure, because virtually every single AI infrastructure developer is either a technology company or a utility or a national entity that has made significant and explicit, repeated, voluntary commitments to manage climate or carbon. And so what does that mean? I think you're going to start to hear more about the carbon intensity of the megawatt hours that are feeding AI infrastructure. It is going to be part of virtually every one of those major FID or financial investment decisions to build. I think you're going to see it as part of the decisions to either augment or create new energy infrastructure with the AI infrastructure. And then, of course, the third leg of that stool, underneath all that will be the triad of carbon, water, and waste. We see lots of deals in the Americas, in Europe, in the Middle East, and now in Africa. We've got a significant partnership with Microsoft. Pay close attention to the announcements they make about AI capability development. It's not just about the AI infrastructure, it's about the grid, it's about water, it's about training. We are going to be a cyber-physical species going forward. Robots are not going to be friends. The future isn't for digital. It's going to be us with these systems. And I think the way it works is hand in hand. Optionality in the energy system will create optionality in AI infrastructure, and then you have the chance of this sort of very powerful symbiotic relationship where what comes out of the AI infrastructure can help plan new critical infrastructure, and that new critical infrastructure can actually be more climate resilient or community encompassing. But we've, again, got to see the energy as the twin, if you will, to the intelligence that's coming out of the systems.
Yeah, you touch on a good point that not only is AI a huge load source for the grid, but it's a tool that we can be leveraging. And I imagine, Pablo, that you're, within your organization, leveraging AI to perhaps optimize power flows. You're still bound by the laws of physics, but how much is AI entering into your calculations?
Well, certainly it's one element. I think the large-scale development of data centers increases the importance and the priority of all of the problems that we have been, or all the challenges that we have been mentioning. Especially considering the magnitude of the development. It also provides an opportunity to do things differently, because the scale is so significant. Then one could make not just a small incremental investment in thinking differently or adapting new processes, but there's a scale to make real change. So let's take advantage of the opportunity.
Yeah.
Yeah, data centers.
Yeah.
How
many do you want, Lisa?
We'll take them all. I mean,
You'll take them all?
Yeah.
Okay.
Massachusetts, right, is unique. It's right, a climate hub of the U.S. and what we're seeing, right, is a lot of co-located data center requests. So not standalone huge data centers. We likely will. Maybe we'll see it in Massachusetts, but we have the limitation of land. There's not a heck of a lot of land available. So what we've been seeing is more co-located applications. So what we've been doing, right, connecting them, top priorities. So one, getting out in front, understanding where they're going to be showing up. And so that's, we have a whole team of customer account managers that are working closely with their different businesses that we're connected to understand who and where is this going to show up. And then it's also providing more visibility for our grid. Like so we're looking at how can we show that doesn't break, CII confidentiality, system information. Like how can we show where is a good spot to connect? Where do we have capacity? Because they can move faster, they can build faster than we can. So how can we get ahead of it? How can we point them in the direction? How can we share with them what the interconnection process looks like? Because when they do connect, we need to understand what the impacts are on the system to make sure there's no outages and consequences to that connection. So there's steps that we need to take to make sure they can safely connect. So it's getting out in front, understand where it's showing up, giving them visibility to our system to help if they are trying to site a new location, close to transmission is good, right? Far away from transmission, not good, right? Because that's when we'd have to build the skinny long line, which would take time. And then flexibility, right, is the other key factor. So, how can we connect them in a flexible manner? On the DG side, the distributed generation side, we do have some pilots and some projects that we're proceeding with now that allow for flexible connections. And what that means is it curtails the customer at a certain period of time to avoid upgrades. And that might just be a few hours a year. It could be 50 hours a year. It depends where they connect. So it's flexibility on our side, but then also on the data center side, because when data centers are actually training AI models, that's a huge load, right, that shows up on the system. So if that can happen, where there's enough capacity on the system, then then we can likely connect them faster with some constraints or some schedules of operation. So that's
the connect and manage.
Yeah, connect and manage, exactly.
Yeah, I'll just give a plug for some research that will be coming out soon. We're working on trying to understand how flexibility impacts system costs and emissions and so on. And it obviously varies a lot depending on where you are in the country. That's another thing that when we think about data centers, we're kind of taking their physical location as given, but can we be better at optimizing the placement of data centers? Is a big open question. So clearly they didn't give us enough time. We have a lot more than an hour's worth of material. So I encourage you to talk with our speakers during the break. And I thank you for all of the valuable questions. And let's give a round of applause to our panelists.